here is Kelvin Sherlock, who's going to tell us that thing.
Okay, so you want to write an FST, File System Translator. Does anybody want to write an FST?
It's an FST.
It's a File System Translator.
What he said.
What I said. So, it's a 2GS thing, GSOS. So the application, when it wants to do disk-related things, calls GSOS, which then calls the File System Translator, which then calls the device driver to actually read blocks on the device and whatnot, and then it goes back to the FST, back through GSOS to the application, and that's how you read and write files. So the history, if we look at it, System 1 was mouse desk. Nothing going on there. System 3, we finally had ProDOS 16, still monolithic. Then with System 4, we had GSOS, and that introduced the ProDOS FST, the character FST, and the High Sierra FST. Then with System 5, they added an AppleShare, File System Translator. Then System 6, we had DOS 3.3, HFS support, and the Pascal. Then in 601, we had MS-DOS, not 3.3, just MS-DOS. And it's interesting, if you look at the actual timeline of when Apple started working on them, the AppleShare should have been included with System 4, then System 5 would have included the legacy Apple II, file systems, DOS 3.3, and Pascal. Then System 6, externals, Macintosh and MS-DOS support. But Apple was a little slow, I guess. So Apple's advice on file system translators was don't do it. They said it's confidential and it will change between system software releases. So they said no documentation is available, and disassembly is not permitted. But Apple's not here, and we are.
Do they not pursue anything like this now? They don't pursue what they regard as violations of their rules?
Shh.
Oh.
What would they do to us?
Yeah, they might kick us off the App Store for violating their terms and conditions. So if you, there are some resources available. The Apple IIGS GSOS reference that says how to make the application calls. The GSOS driver reference documents some of the system services that Apple file system translators will need. It's more designed for people writing device drivers, but there is some overlap. Brutal Deluxe had a nice little book on GSOS internals, which documents some of the things that Apple did not document. And if you happen to have a copy of the System 6 source code, that's useful as well. There is a GSOS internal snooper desk accessory included in the System 6 source code, which lets you take a peek at what's really going on. And Apple also had an exerciser desk accessory for making GSOS calls, arbitrary GSOS calls from the desk accessory menu. And I would also recommend looking at my source code. I've written a couple file system translators. Now, you don't have to read all this stuff, but it helps. Thank you. Okay, this is the exerciser CDA. If you can see that, it lets you make arbitrary GSOS calls and see the results. It's very useful if you want to test GSOS calls or how your FST handles them or doesn't handle them. The internal snooper, this is a screenshot of that, has information on the file control records and volume control records and other useful FST-related structures, as well as other things. Apple said it wasn't for distribution, so don't give it away. So the FST has a header. It starts off with 4 magic bytes, FST in a space. Then there's a pointer to the application entry code, a system entry code address, the FST ID, some attribute bits, the version, the block size, the maximum volume size, minimum volume size, maximum file size, the name, and the credits, which will display if you're text booting. So the system entry, on entry X is the call number times 2. There are 4 calls: system startup, system shutdown, remove the volume control record, and a deferred flush. To exit, you exit with a return long. The carry flag indicates an error, and the accumulator is the error number. So on system startup, that is called while booting. Since it's while you're booting, only the ROM tools are available. Disk tools have not been loaded yet. If you return the carry flag, your FST will not be loaded. If you return the carry flag and have a value in your accumulator, it will not load anything at all. GSOS will stop loading and not tell you there was an error. So don't do that. System shutdown is called when GSOS shuts down. Remove the VCR. VCR is a volume control record. We'll talk about them later, but the thing to remember is that GSOS was designed for people running with one floppy disk that needed to take it in and out, so at any given moment your volume may change on you. And at least GSOS is nice enough to warn you when that happens. And deferred flush, if you set up a session so that all your blocks are not written until later, you have the opportunity to write them later. So the application entry, X again is the call number times 2. Being times 2, it's easier to dispatch it with a jump table. Y is the class number times 2, so 0 for ProDOS 16, 2 for GSOS. And to exit, you do a long jump to the system exit vector, and again the carry indicates an error, and the accumulator is the error number, which is generally passed as is back to the application. So this is a list of all the GSOS calls. There are about 56 of them, and these are the ones that the file system translator needs to take care of, and the GSOS does very little for you, so you need to do everything yourself for basically all these calls. So communication between the application, the file system, and GSOS, it happens 3 ways. The parameter block, which is passed from the application to the FST. The direct page, which is used between GSOS and the file system translator and the device driver, and the GSOS service calls. So parameter blocks generally look like this. It's a structure. You have a parameter count followed by a bunch of fields. Some of them are input fields, some of them are output fields, some of them are input and output fields. And they also could look like this because
Is
this
this
is-
C or is it?
Pardon?
C.
Yeah, this is a C structure, but similar for when handled in Pascal or GSoft or assembly. Yeah, same idea. I just happened to copy these.
Right.
So this is a ProDOS 16 parameter block call because your file system translator needs to support GSOS as well as ProDOS 16, and GSOS does very little to help you out here. So the difference is GSOS has a parameter count, which makes it expandable, and if you're not interested in all the parameters, you don't need to request them. And in the future, if more parameters are added, you can request them. GSOS strings use a 16-bit word to indicate the length, whereas ProDOS 16 were Pascal-based and used a single byte, which limited them, of course, to 256-byte path names. The date format, GSOS uses the 2GS hex time format for dates and times, whereas ProDOS 16 used the whatever ProDOS happened to use in its directory entries. Not very inventive there, are they? And the path delimiter, ProDOS 16 uses a slash, GSOS uses a colon. Why, I do not know. And the direct page at location 0, it's a variety of fields. These are primarily used for the device drivers, and these are documented in the device driver reference. When the FST needs to make calls to the device driver, it fills out the fields and then calls the GSOS service to call the device, which then reads the fields, updates them. At offset 30 are fields which are specific for the file system translator. There's the call number, the parameter block pointer passed in from the application, the device number, 2 device numbers in case of some calls require potentially 2 devices. Then either a path name pointer or a file control record pointer. Then a second path pointer or a volume control record pointer. And we'll get into the file control records and volume control records in a bit. A path flag, which indicates which of the paths are valid. It may be one of them or 2 of them or none of them are valid. And span 1 and span 2, I'll get to those in a moment. Then direct page 80 through D3 is available for the FST to use as it sees fit. So there are approximately 53 GSOS service call vectors. The device dispatcher, for example. These are either documented in the GSOS driver reference or the Brutal Deluxe GSOS internals. So the device dispatcher will call the device. After you populate the direct page locations, it'll call the device to read a block, write a block, and such. There are housekeeping calls related to the volume control record, housekeeping calls related to the file control record. You can dereference virtual pointers, get the system buffer, and I'll get to those in a minute. So there are 2 kinds of FST calls, we could say. There are calls based on path names and calls based on reference numbers. So the path-based FST calls, as their input, they take a path name. So what is a path name? There are a few different kinds of path names we potentially have to deal with. There are absolute path names with either slashes or colons, relative path names, which are actually relative to prefix 0, prefix-based path names, and path names where instead of giving it a volume, we can give it a device name. And the one thing GSOS will do for us is convert them to a canonical format. So ProDOS 16 are converted to GSOS. Any prefixes are expanded. Slashes are converted to colons. If a device name is given, it will look up the device name and convert that to a device number. And if you have a case-insensitive file system based on the flags, it will uppercase all the characters. There's another flag that you want the high bits stripped, so it can do that. It will null terminate at a sentinel 0 to your path name, and it calculates the longest path name component, the span. That is, some file systems have a path name limit. ProDOS will not allow a file name longer than 15 characters. So if you try to open a file with 20 characters long as a name, it can look and reject it instantly instead of going all over the disk looking for a path that cannot possibly exist. So for path name based calls, the GSOS has an FST call strategy here. So if a volume name is provided, it looks for the volume control record and gives the file system associated with it the first shot at handling it. Otherwise, it enumerates through all the file system translators it knows about, and for each one it fills out the direct page location and asks the file system translator to handle it and then returns that result. If it's successful, if it's an error, it keeps going to the next one. And then if nobody wants to deal with it, it returns an error. So for reference number file system translator calls, these are calls made after the file has been opened. There are a handful of them as well, calls. So the strategy here, GSOS will look up the file control record from the reference number, take the reference number, convert it to a file control record, then call the associated file system translator for it. And it provides the call number, the parameter block, the device number where the file was last seen. It could change, mind you, if you have two disks and swap them. Populates the file control record and the volume control record pointer. So the file control record has an ID, which is the reference number, stores the path name, the file system translator ID, the volume control record ID, and then some internal GSOS bookkeeping of the file level that the file was opened at, new line information, the access, whether it's read or write data, and file system. And then after that is FST specific data. And here is an example of a file open. In this case, it's Finder. It's reference number refnum 5 on a ProDOS FST. Volume ID is 1, level 70, and then there's a bunch of internal data at the bottom. Auxiliary data, it stores the storage type, the auxiliary type, and a file, so it doesn't have to look them up each time you're working with it. So the volume control record has an ID, it has the name of the volume, the status, which would mean things like offline or disk switched, the number of open files on that volume, the file system ID that created it, the device where it was last seen, and any FST specific data. And here's an example for the volume hard drive, VCR ID of 1, status 0, it's online, and it hasn't been switched, 4 open files on it on the ProDOS FST. And then bitmap volume header information is stored in the extra information. So memory management, there's a Git system global buffer call which returns 4 pages of direct page space available. Then there's, for allocating memory, you can call alloc seg, alloc VCR, and alloc FCR. The VCR and FCR ones are specific for volume control records and file control records, but the allocate segment is usable for allocating larger chunks for your own purposes. And these do not return a pointer, they don't return a handle, they return a 32-bit virtual pointer, which then needs to be dereferenced with the deref system call. And that takes a virtual pointer and converts it into a 2GS 24-bit pointer. Then when you're done, you can release them. There's a release seg, release VCR, release FCR calls. And if you want, you can use the memory manager. The HFS FST allocate uses the memory manager new handle to allocate direct page space for its 68K emulator. Okay, here's some sample code from my host FST. This is the system entry. It basically checks that the system call is not too big. If it is, it's an error, and then calls the jump table. The system startup call checks to make sure that the global system buffer is where I expect it to be. It shouldn't ever change, but if there's a future version of GSOS, who knows? And the reason for that is because that address is hard-coded on the GS Plus emulator side as well. Then it makes a call to the GS Plus emulator to make sure the GS Plus emulator supports it, and if there's an error, if there's a problem, if it's not supported, it returns with a carry flag set so that the FST will not be loaded. So the application entry is an example. Again, it checks that the system call is not too big. It checks the parameter count maximum. GSOS checks for minimum parameter count errors. It does not check for maximum parameter count errors, so we need to check that ourselves. Then if there's a table I'll get to in a moment that has the maximum P counts and flags for whether path names are expected or file control record and volume control records are expected. Then instead of using the system exit call, I actually push the address on so they can just do a return long. I find that simpler, a little cleaner. And then it uses dispatch table to call the function. So here is the open call, for example. It builds a volume control record because every file control record needs a volume control record. Every file has to be on a volume. Then it calls the host GS Plus emulator to actually open the file and populate the parameter blocks. If there's an error, it exits. The host GS Plus emulator returns a cookie, which is the native reference number, basically file descriptor, which we store into a file control record. So we create a file control record, then update it with the file access, the file system ID, our cookie, and we update the open count on the volume control record. Now, to build a volume control record, we have a hard-coded name for our device, which makes it easy. So we find the volume control, we try to find an existing volume control record with our name, and if it doesn't exist, we create a new volume control record. If it does exist, we need to check if it's whether our FST created the volume control record, which is okay, or if somebody else created it because they stuck in a disk with the same name. And if they did stick in a disk with the same name, we check if there are any open files on it. If there are no open files, we kick it out and create our own. If there are open files, then we give a duplicate volume name error. And this is our table I mentioned. So we have for each call that we support, GSOS call we support, we have a maximum P count and some bits for whether we use the path name or the file control record, volume control record. Okay, this is some sample code from my Minix file system translator. With the host file system translator, all of the hard work is handled in C code on the emulator. But in this case, it's handled within 2GS. So what I want to show here is how I handled supporting ProDOS 16 as well as GSOS calls, since the parameter blocks are different. And the general idea of what they're doing is the same, but the parameter blocks are different. So I use the table-based dispatch, where for each field in the parameter block, I store the offset and a function, the field offset and a function to populate that field. And then I go through that table and update them. I use a macro to actually do it, so code's fairly clean. You don't need this. Okay, one more thing. So, if you want to boot off an FST, when GSOS boots, the bootloader stores a dispatch table at 4 minutes. Okay, I'll skip this and I'll just demonstrate about that. Okay, this is the GS Plus emulator. Okay, here is my host FST. I have a bunch of files on it. Let me show you the native version. Here are the same files on my Windows computer. So I can create files, I can rename files. I can delete files. Stuff like that. So all these files here are actually here. Gone. Okay, and I call it MFS because when it runs on a Macintosh, it is a Macintosh file system. Any questions? This is the GS Plus emulator, by the way. Yes.
Yeah, I missed it. Sorry, I still have. Is there a source online or?
Oh, I'm glad you asked. Yes. So here on my GitHub page, I have a disk image. There's the source and disk images with there's two parts. There's a driver and the file system translator, but they're both included here and the source as well. Nice disk image. There's the driver and the FST. They both are necessary. Yes.
First page. Can you pull up the first page of your presentation? So
Sure.
I can take a picture of your meeting room? Or
Those.
there was a GitHub.
These. Yes.
Oh yeah, there we go.
That's GitHub.
Excellent.
What was the C?
So just to take a step back, the host FST allows GS application access when running in an emulator to whatever the emulator is running on.
Yes, there's a folder here on my. So yep, I say here's my shared host folder, and everything in there is available as that volume.
Have you had to worry about the GSOS cache at the FST layers?
No, I have not worried about that. Since we're not actually using a device for reading or writing blocks, that cuts out half the problem, yep, I think, and I haven't worried about the other half. Yes?
How complicated would it be to create a file system translation for modern Mac file system?
On the, HFS Plus or APFS.
What do they call it?
Yeah, APFS is the new one. I think APFS is probably 64-bit and would be even harder than HFS, which is a 32-bit. I have not thought too much about the difference between HFS and HFS Plus. So I'm not sure it's the answer. Probably a lot of work.
I think it's about time.
Okay, that's it.